guys, sorry about the problems earlier today. I don't know, my computer just froze up and said, nah, you don't need to work. So today we're going to talk about 2.2, and remember I said that we're going to see all these differentiation, this limit stuff, and oh, the derivative, it's so hard. We're going to make it easy today. Here we go, basic differentiation rules. Okay, so a constant function, right, is just a constant function, is the equation of a horizontal line. A horizontal line, what's the tilt to it? The tilt or the slope is 0. But remember, all a derivative is a slope. So the slope of a constant function is 0. The derivative of every constant is 0 every time. And this one we talked about last week sometime. If we have a function and it is, I don't know, we'll call this y equals 3x. What's the slope? Remember, all the derivative is a slope. So it's just the m from the mx. So y prime is 3 because that's the derivative or the slope of the term 3x. Now, for constants and linears, we kind of have these memorized. They do apply using this power rule as well. And I could show it, but I'll probably show you that in class as needed when people ask questions. The general rule is, if you have a function, f of x equals x to the n, then the derivative, we bring down that n as an exponent, multiply, and then subtract 1. So, and that's it. Like, we could do all this limit stuff, blah, 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 but all those delta x's are going to cancel everything except for this term. So if we have f of x equals x to the 5th, we'll take that 5, and then multiply by x to the 5 minus 1, don't forget your variable, 5x to the 4th. Now if you'd like to see me prove that, we could do our whole, limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. We could do our little 4-step process here, or we could just trust in these rules, because with the rules, we could use the limit process in general to show that these rules are always going to work. So I encourage you to accept it. If you want to keep using this method, by all means, have fun with that. This on a note card. Know it, understand it, get used to it. Okay, so if we're given a function, and this is any exponent n, given any function, I can rewrite it. That's kind of weird. If we were given f of x equals 1 over x squared, to rewrite it, I would call it x to the negative 2. Differentiate it, I bring the negative 2 down, and then I simplify. Negative 2x to the negative 3. So at each stage, this is the answer I would probably put in the answer box. I'd simplify my differentiate step. I would combine that to make a negative 3. And then the simplify step would be making a positive exponent. And that's assuming we're given f of x equals 1 over x squared. So just turn it into variable to a power. And if we have variable to a power, this derivative stuff is a lot easier than what we made it out to be last week. We're gonna see this again. Don't worry, I'll come back to that. Constant multiplier and addition and subtraction. If f and g are any two differentiable functions and c is any constant, then the functions f plus g and c times f of x are differentiable. So the derivative of a sum or difference is the sum or difference of the derivatives, right? Just like the limits can move into functions and play with them, derivatives do the same thing because they're defined based on those limits. So with this, now we can take care of all polynomials. All right, with the power rule that was on the other page, the derivative, I'm going to give you a different notation. The derivative of x to the n is n times x to the n minus 1. add in these two rules, we could take care of every single polynomial or polynomial-like function. To take this derivative, each term, minus 2x to the fourth, I'm going to put function and derivative. That negative 2 just stays out in front. Right? That's what that says right there. The derivative of c times f of x is just c times the derivative. So I took my c, my negative 2 out in front. I can take the derivative of x to the fourth, bring down the 4. Make sure you write down your x, your variable, to the power of 4 minus 1. So that is what? That's negative 8 x to the third. From my function, I have 4x cubed. My derivative, my constant multiple rule says I can leave that 4 alone. The derivative of x to the cube, using the power rule, I bring down the 3 and subtract 1 from the exponent. So 4 times 3 is 12. Power of 2. A minus 6, that's the function. All right. The derivative is always 0 because it's constant. Constant functions always have a derivative of 0. So you might write it like this as you're finding it, but probably we would just put the negative x cubed plus 12x squared in our answer box. I like the plus 0 because it reminds us that there was a constant there, and that's going to be something that we need to keep in mind all semester long. If you want to, take each piece and find each derivative and then put them in to the derivative function, I recommend it. That way you don't get lost in the middle of some problem. Alright, so check this out. I really enjoy this particular relationship here. Let's take the best graph of sine that I could create freehand, and then let's look at derivatives. Okay, right here, right? The slope of this tangent line, this slope looks like it has a height of 1. The slope of this tangent line is 0. The slope of this tangent line looks like negative 1. The slope of this tangent line is 0, and this has a slope of a positive 1. Well, what function do we know has a height, let's make this bigger, has a height of 1, and then it goes to 0, and then it goes to negative 1, and then it goes to 0, and then it goes to 1. Let's suppose I could draw straight lines. That would be right there. Check this out. Oh, bummer. Alright. On this one I have to use my eraser. I can't be fancy and move it like I do in class. There we go. Oh look, that's the cosine function. Yeah, so if we take the sine function and we look at the slopes of the tangent lines, oh my, we get the cosine function. And we could do this a lot, but here is a wheel of trigonometric magic that you're going to want to know. Alright, so if you have sine of x, the derivative is cosine of x. If you have cosine of x, the derivative is minus sine of x. So if the derivative of sine of x is cosine of x, then the derivative of minus sine of x must be minus cosine of x. And it comes back around again. So as we're finding derivatives of sine and cosine, they all obey this wheel. Alright, so whatever you have, just keep this in motion, and then we'll see it again in chapter 4 when we look at the anti-derivatives and going backwards in this process. And this circle, the same magic trigonometric circle here, will go backwards for us as well. It's pretty cool. Alright, so we're going to use this fact. Alright, we're going to come back to that. Check this out. Horizontal tangent lines. So we know that tangent lines always are going to use the derivative, because the derivative is the slope. It's an h. of the tangent line. If it says horizontal, a horizontal line has a slope of 0. Alright, so a horizontal, you have to be careful how you abbreviate that, tangent line instantly tells us that the derivative is 0. That's it. Alright, horizontal tangent line. It's a fancy way of saying blah 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 blah. Our derivative is 0. So if I want to find the equation, now find where my instructions here might be, find where f has a horizontal tangent line. Okay, so that's what our instructions would say. So in order to do this, we first find the derivative and then set it equal to 0. So first step, the derivative. Alright, let's use our little, here's the function, here's our derivative, here's a little table. 2x cubed, 2 hangs out. The x cubed, we bring down the 3, we subtract 1 from the exponent. So this will be a 6x squared. Our 4x, this is linear, right, because there's no power. So the derivative is just 4. Take the derivative, set it equal to 0, and solve. Well, this is never 0, so I'm going to change our problem slightly. I'm going to introduce a negative sign, because that's what happens when, you use other people's notes. Sometimes it doesn't turn out to be what you want it to be. So we set it to 0 now. Find the derivative, set it equal to 0. So I am going to subtract 4 from both sides. Divide by -6. And I'm going to simplify this, but I'm going to simplify it in a surprising way. I'm actually going to write it as 4/6 still. I'm just going to take care of the negative over a negative. The reason for this is because, I don't know, because I'm lazy, I guess. I don't know. Probably because I'm lazy. We should call this 2/3. My bad. And then we're going to set x squared equal to 2/3 so that x equals plus or minus the square root of 2/3. But we don't frequently report numbers with radicals in the denominator. It's one of those things that just historically is really hard to divide by the square root of 3, since we don't really know what a square root of 3 looks like. Like, go find a ruler that's square root of 3 feet long. Oh wait, no I won't. So this is, if I want to rationalize my denominator, I'll multiply both numerator and denominator by the square root of 3. And these are the x values where f has horizontal tangents. Now, it seems kind of abstract to me, so I'm going to pause real quick so you don't see what I had on my website before. No, it's not porn or anything, don't worry. Yep, now I got to show you. It's just Ancestry. The reason I was going to show you this, I know I say the word porn and then I forget what I'm talking about in class. I apologize. That's why I try not to say that word very often in class. So we had what? A negative 2x to the third plus 4x. So what we found is this point has a horizontal tangent, and this point has a horizontal tangent. Notice the negative 0.816, the positive 0.816. And just to be sure, let's put here x equals a square root of 6. Divided by 3. That's the 0.816 that we saw right here. And the negative value as well. So we were exactly right. We know the exact value of x that tells us where we have horizontal tangent lines. And this is the answer that WebAssign is going to want more than this decimal. Right? The decimal that we see on Desmos, we see on our TI, we see on wherever. We have a calculator that we're using that's not at all graphing. We can verify this. And did you notice on those graphs, what are these places with horizontal tangent lines? It's where it changes. Here the graph is going up, and now the graph starts coming down. Again, here the graph is going down. Once we hit our point, negative square root of 6 over 3, now the graph turns around and goes up. So this is going to be a really important location for us to know as we do more here. So this whole idea of finding horizontal tangent lines, big, 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 big. All right. Woo. Okay. A derivative can be thought of as a change in position. All right, this change in position here is delta s with respect to time, delta t. Okay, so a change in position with respect to time. Think about it. Distance is rate times time, but a derivative is just a rate of change. Changing distance over a change in time. It totally makes sense, right? This is what we think of as a velocity anyway in math. So we might be asked to find the average rate of change over an interval. And this is just the general secant line. Like average rate of change is just 2 points at the endpoints. Let's find the slope in between them. So we'll find f of 1, which is 3 times 1 squared plus 5, which is 3 plus 5 or 8. We'll find f of 2. That's 3 times 2 squared plus 5. 2 squared is 4. 4 times 3 is 12. And 12 plus 5 is 17. The average rate of change. So average rate of change, ROC, will be 17 minus 8 over 2 minus 1. y2 minus y1 over x2 minus x1. Just find the slope. But we can't say, hey, find the slope because it's a quadratic. So we use fancy terms, find the average rate of change. But it's the exact same thing. All right? It's just finding the slope, but now in a more sophisticated way than we did just in algebra. 17 minus 8 should still be 9. 2 minus 1 is 1. So the average rate of change is 9 units per units, whatever our units happen to be here. It's not a real world problem, so I'm not worried about the units here. Similar to the average rate of change, I was going to say as opposed to, but it's not really opposing. Similar to is an instantaneous rate of change. So this is the secant line slope when we have average rate of change. Instantaneous rate of change is value of the derivative at a specific x value. All right, so this is a slope in general. This is the specific derivative. So it's average over a period of time, or it's instantaneous at a certain value. This is what's happening as I click my fingers, which didn't happen very well. So our instantaneous rate of change, we'll find our derivative first. Let's put it over here. 3t squared has derivative 3. And then for the t squared, we'll have 2t, 2 minus 1. And 5 has a derivative of 0. Remember, these are not equal signs. This is the process of taking the derivative. So this is 6t plus 0. From the left endpoint, that's a t value of 1. The derivative at 1 is 6. From the right endpoint of our interval is t equals 2. My derivative at 2 is 6 times 2, which is 12. Notice how in this case, with these values that were selected, with this function and these values, our average rate of change, 9, happened to be right in between are instantaneous rates of change at 1 and at 2. So if this is a ball falling off of a tower, although it's not going down, so whatever. So this is some type of moving object. After 1 second, it has a speed of 6 units per second. After 2 seconds, it has a speed of 12 units per second. So it's speeding up. The average rate of change says, over the course of this interval, it had an average speed of 9, which makes sense because the average of 6 and 12 makes 9. So this one's moving quite smoothly, quite nice. All right, let's find some derivatives. It was supposed to be a let's get ready to rumble kind of thing, but you know, your patience with me is appreciated. All right, so we want to find the derivative. Let's not get fancy. So I'm going to have 3x to the negative 1. Here's my function. Here's my derivative. That's an x to the minus 2. What I wrote, not what I spoke. So that 3 is going to hang out. And then the x to the negative 2, I bring down the negative 2. And then subtract 1. If you want to do a simplification of it over here, absolutely go for it. This function started with negative exponents, so I have 0 problem with answering with negative exponents. 5x, this is a linear term, so it'll be 5. Don't stop. That's 1x to the 1 minus 1, which is 5x to the 0. But what is any power raised to the 0? Anything other than 0 raised to the 0 power is 1. So you can still use the power rule, and it works out for you. And of course, the negative 1 is a constant and has a derivative of 0. So you may choose to write the 0. You might not. I choose not to. All right, so we're going to use a cosine function. Remember, it's sine, cosine, minus cosine. So when I take the derivative, right, prime, that apostrophe looking thing, that's the prime notation. So my function is x squared, not an equal sign. It goes to 2x to the first power minus sign. 1/2 cosine x. I know the 1/2 just hangs around. The derivative of cosine is negative sine. So this is a minus 1/2 of x. Notice I already put the subtraction here, and my answer is negative, so this will be positive. Because I'm subtracting a negative, we'll have addition. You're done. That's it. Now for today, we don't have a division rule. And yes, that will change tomorrow, depending on when you watch this video. Tuesday in class, Tuesday the 8th of February, we are going to have a quotient rule, I'm just telling you. But for now, we don't. And so what we would do is simplify first. This is 3x squared over x minus 2x over x. That's 3x minus 2. This is a linear function. We all know the slope of a linear function is the m. In this case, that's a 3. And the derivative, right, the derivative of 3x is 3. The derivative of a constant term, that negative 2, is 0. All right, so let's do a couple in this whole strategy of given, rewrite, differentiate, and simplify. I'm going to bring my cursor down here. Get a little, let me see. Let me just edit as we go. Oh, that'd be nice. This is really just me taking a breath. Okay, tab that back over. There we go. Okay, I'll quit messing around now. So if we have k of x is x plus a cube root of x. To rewrite it, I would call this x plus x to the 1/3. Cube root, whatever the root is, the index of the root, that's your denominator. And any power on x inside the radical will be your numerator. So we take the derivative. The derivative of x is 1. The derivative of x to the 1/3 is 1/3. That's not what I wanted to put there. So 1/3, and then the x, the variable. But remember, our derivative is 1/3 minus 1. So this will be a negative 2/3. 1 plus 1/3 x to the negative 2/3. And to simplify that, we would have k prime of x equals 1 plus 1 over 3 cube root of x squared. All right, cube root, denominator. X is squared because the numerator is 2, and it's in the denominator because of the negative exponent. All right, same idea here. G of x equals 1 over x minus 1 over x cubed. I can rewrite that as x to the negative 1 minus x to the negative 3. When I take the derivative, I will have a really hard time in my head, so I had to write it first. The derivative of x to the negative 1 is, bring down that negative 1, and then it's x to the negative 1 minus 1, right? So we always subtract 1. So this is negative 1 x to the negative 2 minus sign. I brought down the negative 3, x to the negative 4. So if this is subtracting a negative, oh my goodness, my head hurts. These ones started with positive exponents, so we simplify it back down to positive exponents. And I'm going to throw a g prime of x on the end over here. Alright. We are at 28 minutes already. I'm gonna trim out about a minute of that for some stuff that kind of went off the wall, and then I might have cussed a little bit. But I'm gonna stop here with the examples. I think the examples that we've done are sufficient for your homework. You're going to have a couple questions on the homework. There's no doubt about that. There's one problem in particular that pretty sure we're going to be looking at in class. But we'll look at that probably on Wednesday. I want to give everybody a chance to look at this video since I'm late posting it. Get this video up. Y'all can take a look at it. We'll talk about it a little bit tomorrow along with product and quotient rules of section 2.3. And you got this. Like, seriously, you survived the limit definition of the derivative. This ain't nothing but a thing for you. Alright, I'll see you in class tomorrow if you're watching this today.